Welcome to the classroom for today's explainer. I am absolutely thrilled to guide you through what is, honestly, one of the most awe-inspiring phenomena our natural world has to offer: auroras. We often call them the northern or southern lights, and these stunning, dynamic displays in our night sky are actually the result of this intricate, invisible dance of particles and magnetism. Today, we're going to set the stage for an epic cosmic journey. We are tracing these lights all the way from their explosive origins out in deep space, right down to the colorful ribbons that dance right above our heads.
But before we literally launch into orbit, I want to throw a question out to all of you students watching. Where did the northern lights actually come from? It's so easy to just look up and admire the view, right? But the true origin of these mysterious lights challenges a lot of our everyday assumptions, because they don't start in our atmosphere. They aren't weather, like rain or snow. To find their true source, we actually have to look roughly 93 million miles away. So, here's the roadmap for our scientific adventure today. First, the solar wind's journey. Then, the chemistry of auroral colors. Next, myths and other planets. After that, rockets, balloons, and science. And finally, how to view auroras yourself.
Let's kick things off with part 1, the solar wind's journey, from the sun to Earth's magnetic shield. Space weather is basically this massive, precise chain reaction. Step 1, the sun releases solar wind. Step 2, this wind travels all the way across the solar system and slams into Earth's magnetosphere, which is our planet's protective magnetic shield. It deposits and just builds up energy right there. And then, step 3, when all that overloaded energy is finally released, it dumps straight down into our upper atmosphere. And that exact precipitation of energy, that's what creates the auroras.
So, you might be wondering, what exactly is the solar wind? Well, it's the continuous outflow of charged particles from the sun out into the solar system. The sun isn't just a static ball of light. It's a seething, dynamic body, and it's constantly radiating its energy outward as this intense stream of magnetic fields and energetic particles. Which means the very material creating those beautiful light shows on Earth was literally born in the roiling interior of our sun.
When that solar wind finally reaches us, I want you to imagine a strong breeze violently flapping a flag. That is exactly how the solar wind buffets Earth's magnetic shield. Our magnetosphere, which gets its power from the churning molten metal core deep inside our planet, takes the absolute brunt of this cosmic wind. The charged particles from the sun flow around Earth, stretching our magnetic field out behind us like a long wake of a boat. Without this shield, those harmful charged particles would hit us directly. But instead, they interact with the shield, which funnels all that energy right toward the north and south poles.
Moving right along to part 2, chemistry of aurora colors, the exciting life of atmospheric gases.
Okay, so once that energy from the magnetosphere rains down into our atmosphere, core physics takes over. These highly energetic space particles start bombarding the gases floating high above Earth. And when these space particles collide with the atoms and molecules in our atmosphere, they give those gases a boost of extra energy. In physics, we say the gases become excited. But, they can't hold on to that high energy state forever. When they eventually calm back down, all that extra energy gets released as tiny specks of light. And millions of these tiny specks lighting up all together, that's what gives us the glowing aurora.
Think of the night sky like a giant decoder ring, because the colors of an aurora, they aren't random at all. They literally reveal exactly what kind of gas is being hit and how high up it is. So if you see red, you're looking at oxygen being excited very high up, like at least 120 miles above the surface. Green, which is for sure the most common color, is also oxygen, but it's sitting slightly lower, between 60 and 120 miles. But check out nitrogen. Excited nitrogen gas in that exact same 60 to 120 mile range glows blue. And if those particles happen to smash into nitrogen really low down in the atmosphere, below 60 miles, you get this gorgeous reddish purple or pink glow right at the bottom edge of the aurora. It is literally a massive glowing chemistry experiment.
Let's jump into part 3, myths and other planets, perspectives across time and space.
It's amazing how geography completely changes our perspective on things. Take the ancient Romans, for instance. The word aurora is actually Latin for dawn, and was the name of the Roman goddess of the dawn. Because those ancient Europeans lived pretty far south of the Arctic Circle, they usually only experienced auroras as a very faint red glow on the northern horizon, which looked pretty much exactly like a reddish dawn. So aurora borealis literally translates to northern dawn. But contrast that completely with the Inupiat peoples of northern Alaska. They call them Kuguyat in their language.
Because they lived right beneath the auroral oval, they didn't just see some faint red glow. They actively lived with, observed, and documented these incredibly dynamic, brilliant ribbons of light for thousands of years.
But hey, Earth isn't special in this regard. Auroras can happen anywhere a planet's magnetic field lines meet its atmosphere. Our spacecraft have captured auroras on Jupiter, which were first spotted by Voyager 1 on the dark side, and then later studied by Galileo, Juno, and the Hubble Space Telescope. The Cassini mission watched them dance over on Saturn. The MAVEN mission found them on Mars, and Pioneer even discovered them on Venus. Turns out, the universe is just full of space weather.
All right, on to part 4. Rockets, balloons, and science, the tools of the trade.
So the absolutely crucial point in studying auroras is getting your instruments to the exact right altitude. Enter the sounding rocket. Now, unlike those massive rockets that carry humans to the moon, these are much smaller rockets completely packed with scientific instruments. They launch directly into the sky, arcing anywhere from 30 to 800 miles high, slicing right through the aurora before coming back down. For instance, there was a NASA-funded mission called GREASE that launched a sounding rocket directly into the aurora over Alaska to study specific structures in the light. They were looking at these classic curls that literally look like swirls of cream in a cup of coffee. They fly their tech right into the action. But, rockets are fast. Really fast. If scientists want a long, steady view, they turn to scientific balloons. NASA's balloon program launches these huge balloons high above most of the atmospheric clouds to get a crystal clear, steady look at the aurora's dynamics. And what's incredibly fascinating is a mission called Balboa. They actually equip these high-flying balloons with infrared cameras to observe how auroras behave during the daytime. That's right, auroras happen during the day too. The sun is just usually way too bright for our eyes to see them.
Now, I want you to lock this number into your brain, 250. That is exactly how many miles up the International Space Station orbits the Earth. Now, if you remember our color matrix from earlier, the auroras happen between 60 and 200 miles up. Think about that for a second. That means astronauts aboard the ISS don't look up at the auroras, they actually fly right over them and sometimes straight through them. The space station has high-definition cameras on board, and astronauts regularly capture these absolutely breathtaking photos and time-lapses of glowing green and red rivers of light passing right outside their windows.
Which brings us to our final section, Part 5, How to View Auroras. Your turn to look up.
If you take absolutely nothing else away from today's explainer, please remember this. Digital camera sensors are incredibly sensitive and can even allow you to record auroras you can't see with the naked eye. Seriously, you do not need a massive, expensive telescope. Modern smartphones are incredibly powerful scientific tools. If there's a geomagnetic storm happening, even if the night sky just looks a tiny bit milky or dark to your own eyes, pull out your phone, point it north, and take a long exposure photo. You might be completely shocked to see vibrant greens and purples pop right up on your screen.
And what should you do with those awesome photos once you take them? Well, you can actually help professional scientists through the power of citizen science. There's a brilliant NASA-funded project called Aurorasaurus. They rely on people just like us to submit our aurora sightings right from our backyards. Every single verified report gives scientists a crucial data point to help model space weather. In fact, participating in open collaboration projects like this can actually lead to newly published scientific papers and entirely new cosmic discoveries. So the question is, are you ready to turn your smartphone to the sky and become a citizen scientist? Today, we've tracked the insane journey of charged particles from the belly of the sun across millions of miles of empty space, crashing into our magnetosphere, and raining down to light up oxygen and nitrogen in a spectacular chemical light show. We've seen how ancient cultures and modern spacecraft have tracked them across time and the solar system. Now, the next time space weather strikes, it's your turn to step outside, look up, and be a part of the discovery. Because after all, when you look at an aurora, you aren't just looking at pretty lights. You are watching our planet's invisible shield actively fighting off a storm from a star 93 million miles away. Which really makes you wonder, what other invisible cosmic battles are happening right above our heads? Thanks so much for learning with me and today's explainer.